back to stats, everybody. We are going to get into our next set of inferential statistics in the section on looking at mean differences in data. So the first set of stats we studied that were in this section were the t-test, looking at the differences of exactly two means. Now we're going to deal with some set of statistics that deal with having more than two means, and if you want to look at differences between them. So these two statistics you're going to learn here are called the analysis of variance, or ANOVA for short. So what we're going to do in this section is, since we're introducing ANOVA for the first time, we're going to talk about the basics of the analysis of variance, what it is, how it's working, its logic behind it, and then we're going to cover the first kind of ANOVA called the one-way ANOVA. So let's get into some ANOVA basics here. Very important things to have at the foundation of understanding how ANOVA works. So to remind you, a t-test looks at the difference between the means of two groups. And it can, when you're talking about the variables, it's looking at the effect of one independent variable on one dependent variable. So the independent variable is the one that has our groups, right? So with the t-test, the independent variable has only two groups. Okay, it's categorical, only two categories, and the dependent variable is continuous, the thing that we are averaging up. So to give you an example here that I'm going to use to make the contrast with ANOVA, so the effect of parent gender on the number of hours spent with children. So parent gender has two levels or groups, mother, father, right? And then the dependent variable is the average amount of hours spent with the children. So is there a difference in the average amount of hours spent with kids between fathers and mothers, right? Two groups. Now, an analysis of variance does the same thing like a t-test. It looks for the difference between means, but it looks for the difference between the means of more than two groups. So it's still looking at the effect of one independent variable on one dependent variable. The key difference is that the independent variable has more than two levels, right? It has more than two groups. And with a t-test, the independent variable can only have two groups. But if you have more than two, 3, 4, 5, and so on, then you have to use an analysis of variance. So for example, if you wanted to look at the effect of seasonal time of year on the number of hours spent with children, well, seasonal time of year has 4 levels, right? There are 4 seasons in a year: spring, summer, fall, and winter. So if I wanted to see, is there a difference in the average hours parents spend with their kids between the 4 seasons, I would have to use an analysis of variance, because that is from 4 different groups. Now let's talk a little bit about the logic of the analysis of variance, how it is kind of what idea is it setting forth for us. Now, the analysis of variance determines if the means of more than two groups are significantly different from each other. Now, how does it do this? It does this by accounting for two things: the variance between the groups and the variance within the groups, okay? So if I have 3 groups here, right, 3 samples, and I got 3 sample means, okay? The first thing that ANOVA does is it looks at how different the groups are from each other. That's what variance is. You remember variance, variability, how different that they are, okay? So it's looking at how different the groups are from each other, from group 1 to 2, 2 to 3, and then 1 to 3. If you add another group, then you have to look at all the different comparisons as that as well. The more groups you have, the more comparisons you would have to make. Now the second thing that it looks at is within group variance. How different is each group from itself, right? How different are the people in group 1 from each other, and how different are the people in group 2 from each other, and so on and so forth. So between group variance is when we are looking at how different the groups means are from each other. Now, the more different the group means are from each other, the larger the between group variance is going to be. Now, between group variance, the number that gets calculated to represent between group variance represents the effect of the independent variable on the dependent variable, and it also includes sampling error. Now, the between group variance will increase if the effect of the independent variable is larger and if sampling error is larger. Now, within group variance, when we're looking at how different the group members are from each other, the larger the variance within each group, the more different the group members are from each other in each group overall, the larger within group variance is going to be. So what is the reason within group variance would increase? It would only be due to sampling error. So how does between group variance and within group variance come together in an analysis of variance? So here's how we can tie things together. An analysis of variance essentially takes the ratio of how much between group variance do you have compared to how much within group variance you have. Now, the idea here, just to kind of speak as simply as we can, if your independent variable has no effect on your groups, then the ratio of between to within group variance is going to be 1. So look at the bottom comparison here right below that second point to illustrate this. So between group variance, remember, is sampling error plus the effect of the independent variable. And within group variance is just sampling error. Now let's say that you calculated sampling error in some data and you got exactly 1, right? Nice clean number. And let's say that you also calculated the effect of the independent variable and the effect was 0, okay, indicating that there is no effect. Well, when you take sampling error plus the effect of the independent variable and you add them together and then you divide it by sampling error on the bottom, you're going to get a result. That's going to be the ratio. So if the effect of the IV is 0 and sampling error is both 1, well then you get 1 plus 0 is 1, divided by 1 is 1. So when the IV has no effect, the ratio of between to within group variance will be 1. Now, if the independent variable has an effect, then the ratio will be greater than 1. Take a look at the comparison at the bottom of that third point. Let's say the sampling error is again 1 on top and on bottom. But let's say that the effect of the independent variable comes out to be 2. Okay, well, we're going to take 1 plus 2, which is 3, on top, divided by 1, and we get 3. So we see that the ratio is greater than 1, indicating that the IV is likely having an effect on the DV. Now, when we learn how to calculate the statistic for ANOVA, this is kind of the logic behind how you would interpret that number. There's going to be in the equation a top part and a bottom part. The top part is representing that between group variance. The bottom part is representing that within group variance, so to speak. So when you take the ratio between and within in that equation, and the result you get a single number. That number, right? The further that number is from 1, or from 0, but let's say 1 for the sake of this slide. The further it is from 1, the more of an effect the IV may be having on the DV. Okay? So that is the logic behind the analysis of variance. It is looking at how different the groups are from each other and how different the groups are within themselves and comparing those two measurements to each other. Now, a few more things about the analysis of variance is that the ANOVA is what's called an omnibus. Okay, the key word here in omnibus is omni. It's a prefix that means all. It's a similar prefix used in words that describe some of the attributes of God, like God is usually referred to as omnipotent. So omni and potent, omni, all, potent meaning power, so all powerful. It's also referred to as omnibenevolent, right? Benevolent good, omni all good. So ANOVA is an all-encompassing type of statistic. It looks for an overall difference between your groups. And because it does that, 1 or 2-tailed tests don't apply. So unlike t-tests, where we had to worry about 1 and 2-tailed and non-directional and directional, ANOVA will always be non-directional, and 1 and 2-tailed test doesn't even factor in, because we don't have to worry about that idea there. So ANOVA is just looking at an overall difference, just wants to know, is there a difference somewhere between your groups? But ANOVA cannot determine where the difference is, if there is a difference. Okay, I don't know if ANOVA doesn't tell me if the difference is between group 1 and group 2 or group 3 and group 4. All it tells me is that there is a difference. So you would have to use something called a post hoc test to determine where the difference is, if there is one. Now, you won't learn any post hoc tests in this class, but if you were to take a more advanced stats class, you might learn some of them, and they would go after you do an ANOVA. So you kind of do an ANOVA to find out where is there a difference, and then you do a post hoc test to determine where the specific difference is. Now, there are 2 types of analysis of variance that you'll learn in this course. There are more than 2, but these are the 2 basic ones. The simple or one-way ANOVA, looks at the effect of one independent variable on one dependent variable, and the IV has more than 2 levels. Okay. Now, the second one that you'll learn after we're finished covering the one-way ANOVA is called the factorial ANOVA. It's also called the two-way ANOVA, but I just refer to it as the factorial. Now, it looks at the effect of at least 2 independent variables on one dependent variable. So you're throwing another IV into the mix, at least one other, right? At least 2, maybe more. And each independent variable has to have at least 2 levels. So with a factorial, the IV can have 2 levels, but it has to have at least 2. Sometimes it can have 1, but it will usually always have at least 2 levels. Now, using our example of seasonal time of year and parent gender and hours spent with kids, you can kind of see the difference between these two ANOVAs here using this table here. And the one way, you just have one independent variable, seasonal time of year. But with factorial, you see the 2 independent variables listed there, columns being the first one, rows being the second one. And then we want to see, is the average hour spent with children different between all the different combinations of the independent variable? It kind of echoes back to the chi-square test of independence when we were looking at a table and all the different combinations. It's similar in that respect. So if that helps you understand the factorial more when we get there, then by all means use that thought process. But let's jump into the one-way ANOVA now and get specific on how it works. Okay, so let's talk about the what and the when. We already kind of talked about this, so I'll just review this briefly. The one-way ANOVA looks at the difference between the means of at least 3 or more groups. Okay, it has to have at least 3 or more than 2, right? So at least 3 or possibly more. One IV is being assessed for its effect on one DV. So those are the situations when you would use it. If you have 3 or more groups and you have one independent variable that has those 3 groups and one dependent variable, you would use a one-way ANOVA. And remember, with a one-way ANOVA, the IV is categorical and the DV is continuous, right? The DV is what we are averaging up, it's what we are measuring. The IV is our group maker, it is our categories. So here's the scenario that we're going to use to understand this a little bit better. So let's say that you ask this question: does feedback have an effect on self-esteem? Okay, does feedback have an effect on self-esteem? So we have that general question, so how can we make it more specific for our research question? So the research question would be phrased like this: is there a significant difference? So there we have, is there the difference between the average, keyword because we're dealing with means, average self-esteem scores for positive, negative, or no feedback? So here's the characteristics. 1, you're looking for a difference. So you know it's got to be one of the mean difference stats, t-test or ANOVA. You've got 3 or more groups listed there, positive, negative, and no feedback groups. And you would see that in your data set. You would look at, well, what are the different groups that I have for this self-esteem variable, okay? Or I'm sorry, for this feedback variable. So if you got 3 or more, it's got to be an ANOVA. And since you only have one IV and one DV, you got the one-way ANOVA. Now, when you're writing out the question, what you need to do is say the average dependent variable name, so average self-esteem in this case, and then list out the groups of the independent variable followed by the name of the independent variable. So we have, is there a significant difference between the average dependent variable, self-esteem, scores for group 1, group 2, group 3, positive, negative, no, independent variable feedback. So that's how we want to phrase that question. Now, with your variables, how do we identify the independent and dependent variable? Very similar to how we did it with the independent and paired samples t-test. So the IV is going to be our categorical variable, it's going to be our groups. So we see that feedback is the one here that we're trying to see, does feedback have an effect on self-esteem? We've got 3 groups of feedback, positive, negative, and no. So we can represent that there with 3 groups with slashes. Now, what is the variable that we are averaging up? That would be self-esteem scores, right? Let's say that we give everybody a self-esteem questionnaire and their final score rates on a 1 to 10, 1 being very low, ... 10 being very high. So we want to know, is there an average difference? Is there a difference between the average self-esteem scores of the positive feedback group versus negative feedback group versus no feedback group? So there we have our variables. Now, when you're calculating the one-way ANOVA, you're going to follow the same logic that you did for the t-test and for the chi-square. It's the same logic. You're going to do a calculated score. You're going to compare it to a critical score taken from an appropriate distribution. So the t-test, you had t-scores and t-crits from the t-table. With an ANOVA, you have a stat that you calculate called the f-test or the f-score. So you're going to compare it to an f-crit taken from the f-table. Okay, so let's put this together so you can see how the one-way ANOVA works in its calculation. So let's say that you got 15 people who are equally assigned to one of the 3 feedback groups. So you're going to have 5 people in positive, 5 in negative, 5 in none. And they complete a written assignment. After receiving their assigned type of feedback, they complete a self-esteem questionnaire. Okay, so they do their assignment, they get their feedback, and they're handed back. They get to look at their feedback, and the ones in the positive group are going to get positive feedback. Oh, you did such a good job. You're the smartest person I've ever seen. Negative feedback is going to be, I don't even know why you try. You should just stop now. And the no feedback would just have no response at all, no marking whatsoever. Then they take a self-esteem questionnaire. How good do they feel about themselves after they receive their feedback? Depending on which type they received for which group they're in. So in order to could do an F-test, we have to calculate how much variance is between each group and how much within each group. And this gets a little technical and it's a little lengthy, but I'm going to break it down, walk you through it easily and clearly. So first we have to look at something called sum of squares. So you've got 2 sum of squares that we have to calculate here. So you have sum of squares between the groups, which is essentially representing the average difference between our group means. And then you have sum of squares within the groups, which is representing the average difference between the scores within a group. And it's one number that's kind of representing the differences within each group across all of the groups, right? Kind of taking an average of how much over all the groups, how much are the people different from each other within each group. Now, between measures the difference between the group means, and within measures the amount of sampling error. Okay, so let's get our calculations for SS between and SS within. Okay. Now I just want to walk you through this. It's a little bit complicated here. I know with you seeing all the math. And so I encourage you to pause the video and kind of look through the symbols here. There are symbols that you've seen before, like sum of, and you've seen squared and things like that. The only thing you probably haven't seen is that sum of t squared over j. Essentially, that's just a symbolic notation for taking the sum of x and squaring it for each group, and then summing all of those together, right? So you have the sum of x squared that you see there in the table at the bottom. You're just going to take those 3 scores and you add them together, and you should get the number that I showed you there. Okay. So when you do this math here, what you get is a SS between of 43.33 and an SS within of 30. Okay. Now, once you have those numbers, you can move on to the next step. After calculating sum of squares, then we need to calculate something called mean squares. So mean squares represents the variance between groups. Okay, it measures the group differences, and MS within represents the variance within groups. It also measures sampling error. Now, why is it that we have to use this thing called mean squares? We can't just use sum of squares. Well, remember that we have to find a way to ensure that our sample is approximating the population it was drawn from. This is what mean squares helps to do. So the way it does this is it is calculated using degrees of freedom. Okay, so degrees of freedom, remember, is that number that ensures our sample is staying close to the population. So what we have to do to find our mean squares is we have to take the sum of squares divided by the degrees of freedom. We have to do this for between, and we also have to do this for within. Okay, so in order to find our degrees of freedom, we have to have a few ingredients. We need big N, which is our total sample size. We have little n, which is the size of each group in our sample. And then we have K, which is the total number of groups. Okay. Now, you can see here, just if you need a second, pause the video and review these numbers here. What we can see here is that the degrees of freedom between is 3 minus 1. So we have 3 groups minus 1, so we get 2. So you take SS between over 2, and you get a mean square between of 21.66. You take the total number of people, 15, minus the number of groups, 3, so you get 12. So you take SS within 30 over DF within 12, and you get 2.5. Okay, so we have mean squares between and within. We got our numbers there. Now, once you have your mean squares between and mean squares within, now we have our ratio. We have our between group variance, and we have our within group variance. Now we can take the the division between them, and we can get our F-score, which essentially is our ratio. It's our ratio between group variance to within group variance. So the top part represents our difference between the group means, and the bottom part represents sampling error. So therefore, our F-score represents the statistical difference between multiple group means while factoring in sampling error. So in a one-way ANOVA, the F-score is specifically representing the difference between the means of our independent variable groups. Okay? Notice how the equation for the F-score is very similar to the T-score, that the top part is the difference and the bottom part is sampling error, and we get one number as a result that represents difference with sampling error. So it's following the same kind of pattern here. Hopefully you can pick up on that. So let's calculate our F-score. Go ahead and pause the video and take the difference between your mean squares between and mean squares within and get your F-score. And what you should have done is taken the difference of the division here, and you should have gotten an F-score of 8.664. Okay, that's our F-score. Now, how do we interpret that? Now, an F-score, again, represents the difference between our multiple group means while factoring in sampling error. So a bigger F-score indicates bigger differences between the group means. Okay. Now, if we have a larger amount of sampling error, it's going to result in a smaller F-score, just like a larger sampling error in the t-test resulted in a smaller t-score. So we want the differences to be what they are with minimal sampling error. Okay. So a larger F-score is due to there being small amount of sampling error with larger differences between your groups. Okay. And so that is essentially how you do the one-way ANOVA. Okay. The basic logic of this will apply in the factorial ANOVA when we get there. And so you can take that, and it's not like you have to learn a brand new one. We're just going to add in another independent variable. It's going to change the math a little bit, but the logic here that you're seeing on this slide stays pretty much the same. Okay. So with the one-way ANOVA, on the next video, we will talk about it in regards to hypothesis testing.